Okay, good afternoon. Let's see if we have questions. All right, so here we have a question about, can you please explain what's going on with the merge and sort? All right, so let me try to explain this. So the merge sort that we've seen in the book is recursive. So we're given an array, then we recursively sort here. We recursively sort here. And then we can call merge to put the two pieces back together. And so one of the questions was, why do we have to have two arrays? So why do we need those temporary arrays in merge? So it would be nice if we could just merge in place, but no one knows how to do that. So if you just look at two sorted arrays, let's say 1, 4, 9, 3, 2, and then 11. Well, no, let's not do 11. Let's do. Okay, 13, 22, let's have it sorted. And then 2, 9, 11, 13, and say another 13. So it would be nice if we figured out some clever and efficient way of putting the 1 here and then putting the 2 here. But see, if you put the 2 over here, then it conflicts with the 4 that's already there. So what could you do? I guess you could try to shift everything up, but shifting is expensive in an array, because when you have an array and now you want to insert something over here, that means you would have to have a loop that moves all of those elements up. Well, that costs you O of n. That if the array is n long, that's about n operations. And so if you have to do that more than a few times, if you have to do it once for every element, then that would be O of n squared, which now ruins your nice O of n log n. So shifting isn't going to work. So so that's the reason that you need those temporary arrays. Now, copying into the temporary array is not terribly expensive. It's an O of n thing that you need to do once. And when you have the individual arrays separate, then you can dump them all in the right place without having to do any shifting. So the merge method is going to need these temporary arrays. No one has ever figured out a way on how to do the merging in O of n times, or even in O of n log n times, without those temporary arrays. And yeah, no one likes them. I mean, it doubles the amount of space that you need for the algorithm, but that's the way it is. So you need to live with the temporary arrays. And now there's this other question with keeping track of where you are. Well, anytime that you do something in a part of an array, like here, we're breaking the array into two pieces. Well, one of them goes from 0 to n over 2, and then the other goes from n over 2 to n. More or less give a bit of round off. So we're sorting these portions of an array. We don't want to copy them into new arrays, because that's an expense that we don't need to incur. It's much simpler to keep track of the starting and the ending index. And you do need to keep track of, there could be arbitrary numbers. Like over here, if this whole thing is like 1,024 long, then you go from 512 to 1,023. So the bottom one isn't always 0. It could be any odd number. The top one isn't always the full length of the array, because over here we're going from 0 to 511. So either the lower or the upper bound, as you cut this array up in smaller and smaller pieces, could be any arbitrary number at all. And yes, you need to figure out what those numbers are. So what the regular recursive merge sort does is the following. Let's take the array that goes from 0 to 1023. It says, well, I don't know, that's too big for me to sort, so I'm going to break it up into one that goes from 0 to 511 and another one that goes from 512 to 1023. And then it's going to recursively break this one up in one that goes from 0 to 255 and then 256 to 211. And this one here goes from 512 to, oh, I don't know, 700 something. Who's good at math? Thank you. From to 767 and then 768 to 123. And then it's going to break this one up into one that goes from 0 to 127. And now it gets so small I can't write it anymore. So the recursive algorithm takes the long one and breaks and breaks and breaks them into smaller pieces. Now that's all fine, but that's not what's going to help us in homework 5C. In homework 5C, we want to do the exact opposite. We want to say recursion, for some reason, has been outlawed by the government, so we can't use it. And so we want to see how can we solve this problem without recursion. And so the idea is to instead do it from the bottom up. To say we have this big array. And now I'm going to take arrays of length. Let me just say for the sake of the argument of length 2 right now. Although we'll do even better than that in just a minute. So I have an array of length 2. And then I have another array of length 2. It's easy enough to sort an array of length 2. If they're not in order, I just swap them. So let's say they're sorted. Now I have these arrays of length 2 that are sorted. And now I'm going to say, I'm just going to take any of those adjacent ones, and I'm going to use the merge thing to merge them together. So at this point, my size is 2. And I'm going to make a loop that says, go through this big old array and call merge on 0. How does merge work? What's the index in the middle? Is that, I guess that's the top of the old one. So I'll call merge 013, and then I'll call merge 4, 5, 7, and then merge 8, 9, 11, and so on. And that's a loop. So when the size is 2, you do that. So for something, you call merge of I plus size minus 1, I plus 2 times size minus 1, something like that. I mean, I may be off by a little bit with those indexes, but that's the basic idea. And now you increment I to jump 4 further down. You need to figure out when to stop that loop. Now what you've achieved is you now end up with an array that has all segments of size 4 sorted, and you can merge the next step. So this has size 4. The next one of size 4. These are all sorted. And so now you merge these ones into one of size 8. Now there was one person who asked this question on Piazza where they said, this merge routine, I've looked at it in the book and it makes my head hurt. And now I'm supposed to write a completely different merge routine for homework 5C, and I'm just going to give up and become a divorce lawyer instead. So what's wrong with that way of thinking? It's not positive, yes. Might be good for that other chosen career. So that person said he or she was unwilling to write a new merge routine. What's that? My question, why does one have to write a new merge routine? How is merging any different in these two situations? Merging means you take two adjacent pieces in this array, each of which is sorted, and then you put them together into something that's now this combined size, and where the whole thing is sorted. That's what does the regular merge sort, and that's what is used in this non-recursive merge sort. There's no difference. It's the same method. There's no need to write a different merge method. Think it through, and the only change in the merge method was that first line that prints out the from and to just for debugging. But merging is exactly the same. So even if you don't want to understand the merge method, you could just use it and it'll work. All you have to do is you have to schedule the merges the right way. Is there any question about that, or is that crystal clear, or everyone is in stunned silence? Did people not realize this? Okay, well, give me another question on Piazza if you're unsure about this. So you don't tinker with the merging at all. Merging, you can just use that method, and that method will merge. It'll take two sorted arrays and combine them to a bigger sorted array. The only thing that you need to do is you need to make sure that merge gets the right inputs. So you need to figure out which indexes it needs to get. And it's going to be a double loop. In the loop where the size is 2, it's going to look like what I scribbled down here. But then you need to say, well, now the size is going to get 4, and then it's going to get 8, and then it's going to get 16, and eventually it's going to stop. So somewhere here there's going to be another loop that says 4, or maybe while, and it's the same thing. So in this outer loop here, size is 2, and then 4, then 8, then 16, until you reach, something. Yeah.
So if we have it sending, source send the correct printout and the correct numbers to the merge, we just have to, we have half of that, and we just have to schedule the correct ones out of the merge.
Yeah, I don't actually remember what I asked you to do in the draft. Let me look that up real quick. This was homework 5, right? I see. So in the draft, I just had you print out these messages, and presumably the merge routine was empty. And that was because I was jumping a little bit ahead of the lecture that covered it, which was only on Tuesday. But if you got this to work, all you have to do is put in the actual code for merge, and it'll automatically work. There's no extra work. So in this case, if you got the draft to work, you're a copy and paste away from getting the final one to work. If you didn't get the draft to work, all is not lost, then now you know that you can just use the regular old merge method. There's no difference. And you just need to schedule it so that it first merges the smallest ones, and then they get bigger and bigger. Oh, there's one minor twist that I hadn't mentioned, is I said at the beginning here is, assume the size is 2, and then merge the 2s into 4s, but that would require that you actually write yourself a routine that can sort an array of length 2. And that's a complete waste, because we can do that with merging. If you take an array of length 1 and another array of length 1, and now you call merge on that, it's going to sort that group of 2, because it's going to take, whichever one was the smaller of the 2, it's going to put it here, and then the larger one is going to go into the next one. So you don't even have to sort arrays of length 2. Another way of thinking about that is an array of length 1 is always sorted. Is it? Is an array of length 1 always sorted? Well, right, it is. So, that should be your base case. So over here, I said, started with 2, but that was just to make it more intuitive. Really, you should start with size equals 1, and then work your way up to 2, 4, 8, and so on. And when you look here, you see that that's what it does. This one here is a 0, 0. That's one of size 1. Right, here's another one of size 1. So over here, the first ones is where it merges the ones of size 1 into those of size 2. And then it goes on, merges the ones of size 2 into size 4, the ones of size 4 into size 8, and then the ones of size 8 into size 16. That brings up another question that someone asked. Someone said, oh my God, my program actually works if the size is not a power of 2. If I give it an array of size 20, it will work correctly. Should I break it so that it fails to work correctly in these cases? And no. I mean, that's fine, right? I'm not even going to test it. I'm only going to test your program with powers of 2. If it does something else with other inputs, yeah, that's great. Don't break it. In fact, you're going to be in luck because, as it happens, homework 6A is exactly to make it work for everything. So if you have a bit of extra time on your hand, you can already make yours work for everything, and then you have homework 6A out for absolutely free. So in this case here, the non-recursive way, the recursive way is this top-down thing where you cut it up into smaller and smaller pieces, and the non-recursive way just does it the other way around, merging small pieces into somewhat larger ones and so on. And you just have this somewhat unpleasant-looking double loop. So it's easier to understand the recursive way, but the non-recursive way works every bit as good. Okay, did I beat this to death, or do you have more questions? Safe. Oh, how does someone asked, how does the merge method split arrays with an odd number of elements? I don't think the merge method cares. So, get some. The merge method, the way it's written, takes from, mid, and to. And so it has 2 arrays, the ones that go from to mid. And then I'm just going to exaggerate it here. Say from mid to, or from mid plus 1 to 2. And then it copies them into its own arrays, and so it takes the smallest one, maybe from here, then it takes the one from here, maybe then another one from here, then another one from here, and then a few from here. And eventually it's going to run out of elements in one of them, and then it just straight copies all the remaining ones from the one that still has them available. That's what merge does. It doesn't matter whether the 2 arrays, for merge, it doesn't matter whether the 2 arrays have the same size or not. They could be completely different, wildly off. So I don't think that for coding this up, you're going to care. But anyway, in the context of homework 5C, that question doesn't even arise because you know that your thing is a power of 2, so you can always cut it up into exactly even pieces. In homework 6A, yes, you will worry about how to make one of the pieces be a little bit shorter or a little bit longer, and that's just figuring out in which direction to round. But for homework 5C, it's not even a question that comes up. But even if it did, merge does not need to have things of equal size. The reason that we cut things up into equal size is so that the recursion finishes in log n steps. So if we start with 1,000 and then go to the 500s and then the 250s and then so on, then we're done after log of 1,000 steps. If we were to cut it in an uneven way, which is what sometimes happens with quicksort, then you might not be finishing in log n steps, but you might have more steps. So for the efficiency, the cutting it in half or nearly in half is important. For programming it, it's actually not. All right, let's hope that took care of that. Okay. So okay, there's a bug in 6C. Okay, I'll need to fix that. 6B. All right, so someone is looking ahead at homework 6. Nothing wrong with that. So let me see. 865. 8653 28108 8653 28128. So someone wanted to know for this particular array what you need to do in that homework. So to set the stage here, since not everyone has looked at this, we've seen the quicksort algorithm last time. And so what quicksort does is it takes an array and then it wants to partition it into two segments, one that is less equal the pivot, in our case that's 8, and one that's greater equal the pivot. And it does this by swapping things out that are not in order. So in this case here, if we were to just use the regular algorithm, it would this is actually a very unnatural example because they're all less than, but that I'm going to make one of these here into a couple of them larger just to show off the regular quicksort a little bit better. So in regular quicksort, you have an index here, you have an index here, and now you say, all right, this this one here is less, so we're happy. We then go here and here. In this case here, we say, well, this one is less, so we're still happy here, and just move on here until we find one where it's greater than 8 here and one where it's less than 8 here, and now we swap these two. And then we move on here. And now we swap these two. And then the result is 8, 6, 5, 0, 1, 8, what is it, 13, 12, 13, 8. And now look, on the left-hand side, everything is less or equal 8. On the right-hand side, everything is greater or equal than 8. Now we recursively sort, and they're smaller, so we think that we know that sorting can be done. So here's the recursive sorting on the left. Here's the recursive sorting on the right. And now what do I do to sort the entire array? Yes? What's that? Oh, they're already together. So what do I do? Nothing. What I do best. Okay? So I'm already done at this point because everything to the left was less or equal to 8. And it's now sorted. Everything to the right is greater or equal to 8, and it's sorted. And notice that the 8s here, they all match up nicely as they have to be, and everything else is... So I'm done. So that's the genius of quicksort. To do this partitioning, recursively you sort, and you're done. Now, the issue with the partitioning is that when you have lots and lots of elements that are equal to the pivot, and that might happen if you have lots of identical elements in your array, because you don't quite know what the pivot is going to be. And here we just pick the first one. There are other people who pick random pivots. You might say, well, the best thing to do for the pivot is to pick the element that's pretty much cuts the size in two. But to compute that would take so long that you would lose the efficiency of the algorithm. So you kind of have to take a better, just a stab at the pivot. And so in this course, we're just taking the simplest one and say we'll just choose the one on the left. So when there are lots and lots of identical ones, if you have an element with thousands of elements, a good number of them are 8s, then it turns out not to be all that efficient to do this kind of partitioning. But as the homework assignment says, then it would be better to put all the 8s in the middle, because if there are lots of them, say that we have thousands of numbers and hundreds of them are 8, whatever the pivot is, then why even bother sorting them? If we could just group them all together, they would automatically be sorted, and then all we would have to worry is to sort this much smaller array and that much smaller array. So that's is a smart idea, and it'll work when you know that your array has lots of repeated elements, which sometimes happens in some applications. But it turns out that the little algorithm that I showed you that spreads the things apart to the smaller and the greater ones, it doesn't really work well when you also now want to put the pivots themselves into the middle. But it turns out to be easy to do this kind of partitioning, where you say that you put the 8s, or whatever the pivot is, you put those at the ends. And so you have to think through this a little bit, what happens when you move your indexes inwards. There's a few cases that you need to worry about, and I've given you the cases in the outline. So you need to figure out, what do you do when you already have a bunch of 8s here, you have some other stuff here, now you're here, so these are all less than 8. Now you're here with the other index, these are all greater than 8. And there's a few cases. What happens if this one here is in fact an 8? Then what you want to do is you want to swap it against this one. What if this one is an 8? Then you swap it against this one. And what if this one isn't an 8, but it's greater than an 8, and this one is less than an 8? Well, then you want to swap the two. There's like 5 cases, and you need to think through them. And then you move the indexes inwards, and when they meet each other, then you stop. So in that case, you get a partition where you have you have a whole bunch of 8s outside, then you have the less ones, then the greater ones, and then the equals. And now, of course, for the recursion to work, you now need to rearrange it so that all of the equals fall into the middle. And that's pretty easy to do because you know what the pivot is. So all you have to do is you have to copy the less ones. Let me make a picture of that. So you have a bunch of 8s. You have the less 8s, you have the greater 8s, and you have more 8s here. And so what do? You copy all of these ones over here. You copy all of those ones over here. Yes, you're wiping out precious 8s in this way, but that's okay because you know what they are. They're all 8. And then you figure out what you need in the middle here. You just fill all of those things with 8s. So that's a couple of loops. One loop where you make those indexes move inwards and you swap everything, and then the second loop that does this rearrangement. All right, so that one is definitely a fiddly exercise, and was good if whoever asked that question to get going with that early. That surely is the hardest problem of the ones that you see in homework 5 and 6, just because it's all these loops that you need to get just so. Okay, let's see what else we got. Okay, well, I think that takes care of that. If something comes up in the next half hour or so, just put it back on. So let me move on to the lecture. So far we've seen sorting, and we're now moving to a somewhat simpler problem searching, and it's actually something that's just a repeat from what was already in 46A. There's, in general, if you want to search in unsorted data, then there's not much you can do. Suppose that you have a list of student names that are unsorted, that I just randomly get 1,000 emails from people, and now I want to find a particular one in there. I want to find out whether Joe Smith has actually sent me an email. Well, if they're unsorted, I could try to sort them, but that costs some amount of time. So let's say I don't want to do that. So instead, I'm just going to do the brute force thing. I'm going to look at all of the elements in turn and find a match. That's all you can do if you have an unsorted array. What's the cost of it? So let me draw. Okay. If you have n elements in the array, let's say you have 1,000 elements. If the element is present in there, then there's and you don't know where it is. It could be any of those random positions, and on average, it'll take 500 steps. Why 500? Because you might get lucky and the 300th step and find it, or you might not and have to move over all the way to 700 or 800 if it's further in the back. But on average, there's a 50-50 chance that it's in the first half or the second half. On average, it's going to take you 50% of the steps, so 500 steps. But O of n over 2 and O of n are the same, so either way it's O of n. If the element isn't there, so let's say you're searching for an element that's not there in the array at all, it'll definitely take you n steps because you have to check against every one of them to make sure it's not one of them. So it takes, for a successful one, n over 2. For an unsuccessful one, it takes n. Either way, it's O of n. That's the efficiency of linear search. Linear search is just called like that because you just make a linear progression through the collection until you find it. A very trivial algorithm, easy to understand how it performs. So binary search is when the array is already sorted. So let's draw a little picture here. So you have an array, it is sorted. And so now let's say you want to, and let's say it's an array of numbers. And let's say you want to find the number 53. Well, now what you're going to do is you're going to look at in the middle, and let's say in the middle you find a 69. Well, that's valuable information. Because now you say, well, that's a bigger one, so my element must have been somewhere in the first half. See, that's where the sorted comes in. Previously, if you had a random array of numbers, and someone told you in the middle is the 69, that wouldn't have given you any information at all where the 53 comes in. But once it's sorted, you know the 53 must be over here. So you look in the middle of this one, and let's say there you find a 39. Well, then now it must be in this here. So each time you cut the array in half, and eventually you're going to be homing in on a range where with 1 or 2 or 0 elements. That's something we'll need to figure out. There's a devil in the details there. But eventually you get into something that's very small, and then you can directly give the answer. So what's the efficiency? So in the case that the length was 1,000, say, how many cutting in half steps are possible? 1,000, 500, 250, 125. Then my math goes down, but it's going to be log 2 of 1,000. It's going to be about 10. 1,024 would be exactly 10 steps, and so it's just a little bit less than that, but it's rounding up, it would be 10 steps. So if it's n, then it's going to be log 2 of n. And so the general idea is that if you cut in half at every time, that gives you this logarithmic performance. That's, of course, much better. So in this case, if you needed to find something in 1,000,000 values, it would take you 20 steps. All right. So it looks like binary search is better than linear search. 20 steps is better than 1,000,000 steps. Much better. Well, if it's so much better, should you sort? So let me ask that question real quick. Well, that's no good. All right. Okay, I want a few more answers. Okay, while this final answer is trundling in, let's see here. So there is a majority opinion for 3. The second one is this one, and neither of those two is correct. So I think I need to take a bit of time to go through this. So at some point, it's got to be a good idea, right? Imagine those 1,000,000 elements. Every search costs 1,000,000 iterations, if it's a linear search. Every binary search costs 20 iterations. At some point in time, it has to be worth sorting the array to go down from 1,000,000 to 20. Yeah?
No.
So, if you make 1,000,000,000 searches, 1,000,000,000 times 20 is so much better than 1,000,000,000 times 1,000,000 that's going to dwarf the cost of sorting. On the other hand, if you only make one search, then it probably isn't worth sorting, because what's the sorting cost? So the sorting cost is O of n log n. So for 1,000,000, that would be 1,000,000 times 20. So that would cost you, something 20 millions or so operations, and that's probably not really worth it for a single search. But now let's say you make at least n searches. So in this case, the cost, so let's look at the cost of n searches. So if we sort first, we pay O of n log n, and then n times you pay O of log n, because binary search is O of log n. So that's the cost of sort plus binary search, n times. Now if we look at the cost of doing a linear search n times, that's n times O of n. Well, the first one is O of n log n. The second one is O of n squared. Right, n times O of n is O of n squared. That's worse. That's much worse. So if you do at least n searches, you should definitely do it. If you do n squared searches, well, you should definitely do it. In fact, if you do log n searches, you should already do it. Then that's the break-even point. So if you do any more than log n, you should definitely first sort and then search. So that's the answer. And so surprisingly many people Anyone want to explain why they thought n squared? Other than that it sounds good? All right, so think that through and look up in the video, look at the computation that I did, and try to be able to do that with your own scratch paper. Just as a general observation, you see me scribbling these things on here. I wouldn't be able to do these things in the head myself. I always get out a piece of scratch paper and figure it out that way. All right, sorting real data. So whenever you look at textbook, they always show you how to sort integers. Now I'm about to give you a shocking revelation here. I can't remember ever in my life that I got paid for sorting a bunch of integers. Ever. It's just not something that ever comes up. What I always have to sort is file names, search results, like Google might do that, birth records, whatever. And the other thing is, when the time comes that you need to sort something in an actual application program, don't write your own sort routine. Every once in a while, some employer calls up one of the faculty and said, "This turkey I hired from your department, he started writing his own sort routine, and it wasn't any good. Why didn't he use the library sort?" And that's, of course, what you should do. So the reason that I've been bugging you with searching and sorting is not because you will ever in your life use it. You will not. No one will pay you to write a sort function. And if someone offers, you should politely refuse. Someone else has done a much better job already. The reason that we're studying sorting and searching is to understand what makes algorithms fast and what makes them slow. And it's a problem that it's easy to understand. It's easy to understand how the different algorithms work in a problem domain that you're already familiar with. So that's why we're studying sorting and searching in this chapter, not because you would ever implement your own ever again. This has been done 50 years ago. So if you ever need to sort something, figure out how to use arrays.sort or collections.sort. If you ever need to do a binary search, there's a binary search function that you should call. You should not program it by hand. There's absolutely no point in that. So, just a quick question here. So now you're given an array list of rectangle, and you want to sort it by increasing area. You want the ones with the smallest area to the left and the ones with the largest area to the right. Now, there's some rules that have to be fulfilled for you to be able to use these generic methods. So when you call arrays.sort or collections.sort, it'll have to know how to compare elements. And so in the book it goes through this and says, either they're comparable or you supply a comparator. And so I want to know what you should do in this specific case. So should you call arrays.sort? Should you call collections.sort? Should you use a comparable or should you use a comparator? And so that's a pretty basic question. Just put it up. Answers. Hey. Search. So you need to figure out, do you call arrays.sort or do you call collections.sort? And you just have to look at, here's arrays.sort. Somewhere I had collections.sort. Here's collections.sort. What is it that we're sorting? We're sorting in an array list of rectangles. And it'll work with one of the two. Then you need to figure out, does rectangle implement comparable or do you need to supply a comparator? Those are your two options. All right. Does rectangle implement comparable? It doesn't seem to, right? It implements shape, serializable, and clonable, but not comparable. That's unfair. But if you think about it, what does it mean to compare two rectangles? Is this rectangle better than this one? Or this one? That's totally subjective. So there's no standard way of comparing rectangles. So it's not. So that would rule out this one and this one. Now you're sorting an array list, and that one arrays.sort can't do because arrays.sort sorts what? Trick question of the day. What does arrays.sort sort? It sorts arrays and not array lists. So there's only one possible answer here. Let's see. And it's not the one that was the majority opinion. So most people stayed away from arrays. That's good. But the comparable stuff only works when you're sorting something that is actually comparable, such as numbers or strings. They implement comparable. I think file implements comparable. Let's find out what else implements comparable. It's easy enough to do. Here are all known implementing classes that implement comparable. So, most of which I have no idea what they are. But if you happen to have an array list of pseudo column usage objects, you would be in luck. No, I have no idea what that would be. But if you look at it, rectangle is not among them. In fact, most of them, these are pretty weird. Date makes sense, right? Dates are comparable. You can say when one date comes before another. File names are, you can sort those. But things like rectangle or point are not in here because there's no natural comparison for those. That means you have to supply your own comparator, just like you're doing in homework 5A. All right, well, that brings us to the end of the lecture.